Natan, hi, welcome back again.
Thank you so much. I had a wonderful experience earlier this morning.
Great. How do you feel about the conference so far?
I think it's going very well. It's an immense challenge to have 3 live streams online, and you're doing a great job.
Thank you very much for your support. And I want to invite you to our online stage. The floor is yours.
Thank you so much.
Great.
So welcome everyone. My name is Natan Silnitsky, and I'm a backend infrastructure developer at Wix.com. Earlier today, I talked about Wix's event-driven architecture and how we use Kafka, Kubernetes, and gRPC in order to have a fault-tolerant, polyglot, performant distributed system. Now I want to talk about key event-driven patterns that I have implemented and have witnessed implementations of at Wix that allow us to have a distributed system with growing needs of storage and data and traffic implemented easily using these patterns. So Wix has around 180 million registered users or website builders, because Wix is a website building platform, and 5% of all internet websites run on Wix. We have around 1,500 microservices on our system, and more than 1.5 billion Kafka messages are produced every day. So that means a lot of event-driven use cases found from a whole host of microservices that process events. So the event-driven patterns that are used by these microservices that I will discuss today are consume and project, where you have a monolithic service with a giant database that you want to start easing the load from. Event-driven from end to end, how to have events processed all the way from services back to the browser using Kafka and WebSockets. Zero latency key value store, how to utilize Kafka compacted topics in order to have in-memory zero latency key value stores for our services. And events in transactions, how to achieve exactly one semantics more easily by using Kafka solution for exactly once and not needing to implement it yourself for your critical paths when you process events. So once upon a time, there was the monolith, and all of us collectively decided to move from this monolith to a distributed microservices system. So that's great. These microservices are deployed separately. Different teams are in charge of them. They can scale differently in the production environment. So that's very good for a distributed system that is deployed globally. Now, with the monolith, we used to have one big database with a few tables. If we would have used this one with all microservices, that would probably be a bad idea, because it will mean shared immutable state among these microservices, high contention for these access to these tables by all these microservices, and actually a lot less flexibility of choice. This is probably like a relational database, but maybe some of these microservices need a graph database or a NoSQL one. So usually with microservices, the idea is to encapsulate the data, to hide the database from the user of the microservices, and expose the API in order to retrieve data. So that means we have more flexibility, microservices can choose the right kind of storage type for them. And they can also evolve the schema without worrying that that will affect any other microservice because they have complete control over their storage and data. But now that we've done all of these things, how do we perform the communication between these microservices? So here we have a classic e-commerce example. We have a checkout service, and it requires information from the user service and inventory service. It has interactions with the other services. So the classic request reply model will mean that we will have communication done with HTTP or RPC request and get responses back. But do remember that we have decided to hide the database from for each microservices from all other services. So the checkout service is going to need to retrieve the information one by one from all of these services. It cannot do like a join operation on a single database, monolithic database. So this is going to probably be slower. And also we have unreliable networks. So we need to handle any issue with that ourselves in our service to make sure that we get the information that we require. So we can introduce a message broker in between the services that offers high reliability because the broker is clustered. It has multiple brokers that have data replicated among them to handle messages and ingest them. And now our services are completely decoupled, and actually the flow control is moved from the sender to the receiver of the request. Basically, now we have complete control of when to process messages, when to consume them, and we don't care if the message producer has maybe gone down. We are not relying on it. We're relying only on the message broker. And specifically with Kafka, we get a distributed log broker where the topic is divided into partitions that are basically append-only logs. And we get linear scaling because whenever we need to scale up the amount of traffic we move through this topic, we just add more partitions. And like I said, each partition is an append-only log, so it's very high performance. You just scan through the partitions sequentially, as it's just a file, but most of it is loaded into the memory of the broker. And once the message is produced to the end of the partition, it's available for the message consumer to consume. It consumes sequentially. It will commit messages once it finished processing. So it doesn't need to be worried about losing any data. Data can be stored infinitely on Kafka, theoretically, although the default is 1 week. And if you notice here, it seems like we have shared state between the message producer and the message consumer, but that's not the case. It's actually immutable because we have these events. So they cannot really interrupt one another like if two microservices would interact on a simple SQL type database table. So the message consumer can guarantee that it will eventually consume the message, offering higher reliability, because as long as the message is not committed, it will try consuming it again and again until it succeeds. So now with our classic e-commerce example, if we switch it over to the event-driven model, what it will usually mean is that we'll have several topics with user service, cart service, and inventory service, usually producing events to the user topic, cart topic, and inventory topic to be consumed by the checkout service. And then the checkout service will produce order requests to the payment service, for instance, in order to process payments. Now, this is a very high-level view of how the event-driven model would look like with a message broker. But now we'll go over concrete design patterns that we can utilize this and see how we get better architecture for our microservices. So, like I mentioned, we're going to discuss 4 event-driven patterns that we use daily at Wix in our microservices. I've written a few more patterns on my blog posts, and I will share the link to all of the relevant blog posts at the end of this talk. So the first design pattern we're going to discuss is consume and project. So here we have our monolithic service. It used to be monolithic, which is the metasite service at Wix, which handles requests to get a lot of information that relates to websites, including which applications are installed on the site, what's the site current version, who's the site owner. So these are very popular requests that are sent by a lot of my other microservices at Wix, including Wix stores, Wix bookings, and Wix restaurants. So all of these incoming popular requests means a very high stress load on the database, both for read and write, where remember we need to have locking in order to make sure that we get latest information when we read it. And the legacy metasite had one big table with large metasite objects, so that all of these requests all came down to the same table. So the metasite team, what did they do in order to increase the reliability of these flows and make sure that performance keeps up with the growing scale of Wix? They decided to first start focus on just a part of the information that resides in the large metasite object, because it's a very popular information that is required by our verticals. Which apps are currently installed on the site? So the first thing they did is they produced all of the events emanating from this database to the Kafka broker. They created a new event called site updated. So now there's a Kafka topic with all the information about sites at Wix. Remember, it could be infinite amount. The second stage of this pattern is to consume and project. So here they created a brand new service called Reverse Lookup Writer, where they consumed these site update events, but they filtered only events that have site installed apps updates. And only those they actually wrote into a completely new database table that only has the installed apps contacts in them. So they actually projected the data to only contain apps contacts and nothing else. And now we have a new table that potentially verticals can read from, but they decided to split read service from write service. So they created another service that's called a reverse lookup reader that only the requests only arrive to it in order to fetch information on the installed app contacts. So the reverse lookup writer only consumes and writes information. The reverse lookup reader only reads information. And now we'll talk about the benefits of this pattern. So first of all, with consume and project pattern, we mostly produce instead of serve requests, we produce events from the original meta-site service, and we also produce events for the in order to consume them from the reverse lookup. So that means a massive load reduction on the databases and the original monolithic service. And actually, this projection of the app's context means that we actually created a materialized view that is highly optimized for the client requests and queries. So if before that we just had one big table to serve everything, now we can actually easily, with Kafka, create materialized view databases that can be NoSQL, SQL, or anything you want to serve specific needs from our users and different services. And why did the team decide to split between read and write? Well, this way, all the reader service can be deployed across the globe in multiple data center locations in a very small footprint of just reading stuff from a database. And the database can, of course, have read-only replications that also deployed all across the globe, close to the location of the reader's services. So it means that we have much better performance by having these services closer to our users, and also it's easily scalable. We don't need to scale writing to the database from the write service. We don't actually need to scale that so often because reads here happen much more often than writes. And it's a more resilient style because the read request, the contention of the database happens on replicated data. It will not affect write access to the database. Cool, so that was the first pattern. The second one I want to discuss today is to do event-driven style from end to end, browser to first service to the last service. So consider use case where we have a long-running asynchronous business process, something like importing contacts from various sources like Gmail and Microsoft into the Wix platform. So here we have a context job service that is in charge of creating import jobs request. Maybe it decides to split up jobs according to the source of the contacts. And we have a service to actually perform the import jobs themselves. And of course, there could be multiple services here. Now, we could have done this completely in a completely request reply style, where the user starts the import request and it sends the request over to the context job service. But then, because this is a longer running process, we will need to poll the job service in order to get information on the current status of importing. And then the context job service will need to poll the context importing service and update some newly created database table with all the current status information and do optimistic locking and stuff like that in order to make sure that the browser gets correct information on the status. So I offer an alternative pattern here based on event-driven style. So first, the browser is going to subscribe to notifications from the WebSockets service. So it provides a channel identification where the WebSocket service can stream events of notifications back to the specific browser. Then the browser has the import CSV request from the jobs importer. but it can return immediately a response once the message of the jobs are produced to Kafka. And the browser is not going to need to poll anything. So now the consumers of the services that are in charge of doing the import can start consuming the job request and performing the actual import jobs themselves from the Google Cloud, from Microsoft, from anywhere they need to. And once they finish processing or halfway through, they can notify the channel ID, according to the channel ID they get in the job event, notify back to the user on the browser that is waiting for status updates, and they just publish it. They can also interact with the WebSocket service via producing messages to Kafka. So, and these services that are in charge of importing can also be found in various kinds of data centers all around the world, and you can easily replicate the job requests across various Kafka clusters that are found in different data centers easily. So here you can see we have a completely distributed, decoupled environment and system where no polling is done. Everything is done in push style with the event style, and no extra database storage is needed. So like I said, there is no polling. We just notify the user when it happens on any status change. So less traffic also happens on the wire. And it's very scalable. It's really easy to spin up more import job workers. If we see that throughput keeps growing, we just add more partitions to Kafka and more pods. We can do that all around the world. And by using replication, we can do cross-DC requests, very easy to set up. So we have Kafka and WebSockets together helping us achieve a more resilient, more distributed solution for this specific use case. Cool. So the third pattern I want to discuss in this talk is the zero latency key value store. So we sometimes have dynamic configurations, and we want to access them extremely fast because we don't want our business flows to be stuck. So Kafka doesn't only serve as a messaging platform, it can also be a storage platform. So it has compacted topics where the topic messages are deleted not after the retention time has expired, but only if each message has a key and a value in Kafka, each record. So this key and value will only be deleted if a new value already exists on the partition. So this way, we can actually, when we go through and read sequentially a partition, we can actually get, at the end of the partition, the latest values for each of the keys in our key value storage. And at Wix, we created a key value store implementation on top of these compact topics. One part of it is the key value store reader that simply has an in-memory hash map of all of the key and values found in the topic. So when the service starts up, it reads all the sequentially all the information from all the partition, and it builds up the current snapshot in time of the key value store. So it's already read in this example, value v1 for key 1 and v1 for key 2. And once it reads the v2, key 1 v2 value, it just updates the hash map with a new value, and key 3 is added, and so on. And when it finishes, it has the up-to-date information. And of course, updates can keep on coming. So let's consider the following use case where we have the business manager service at Wix that helps with managing all the business information that our Wix site owners have. And it has the countries that Wix operates in key value store. Like to get the drop down for the users to which country it can create a store in at Wix. And we also have the booking service at Wix that helps Wix site owners offer schedules that can be booked. For instance, a yoga instructor that has lessons can offer her services to her customers. So the booking service has the time zones dynamic configuration because it needs to know all the time what is the current time zone in each country. So these key value store readers are backed up by compacted topics in Kafka, a country's topic and a time zone's topic. Now, the business manager also uses another abstraction that we've created at Wix called a key value store writer that basically has a Graham producer, a Kafka producer inside of it. And when it produces and when it needs to add a new country to the list of countries, to the stored countries in the countries topic, it just produces a new message event to the topic where we have a new country, South Sudan. And bookings also needs to know about changing configuration of the country's key value store. So it has the key value store reader we discussed, and it can consume updates on the countries. So bookings have consumed through the key value store reader from the previous slide an event that a new country has been added to Wix, South Sudan. And now it needs to update its own key value store that it maintains about time zones. And it will produce a new time zone for South Sudan. It will produce it to the time zone topic. And now it will be able to access the updated time zones key value store through the key value store reader, where the hash map has been updated with a new entry for South Sudan and the time zone. And for instance, we can also add other services that are interested in time zones. So if bookings updates that Albania has entered the daylight savings time zone, not only will bookings' own key value store reader be able to get information that a new time zone has been updated, but also the event service that manages events created by Wix users, such as conferences like this one. So we can, the event service will also has a consumer on the time zones compacted topic because it uses the key value store reader, and it will also have a complete up-to-date time zones configuration for it to use. So I hope the key value store reader-writer concept on top of Kafka is understood. The key takeaways here is that we're loading the compacted topic into memory, which gives us zero latency key value store that can be dynamically updated, mostly from configurations. Remember that a compacted Kafka topic is still a topic, and other services can consume updates on updated events, whether in the style of a key value store or just processing the events as a regular Kafka consumer. And this zero latency key value store is appropriate for small data sets. like I showed here. For larger data sets, the topic, once a new message is produced, should be streamed to a disk-based database. And on the read side, we can still have an in-memory cache that reads data from the database and updates the cache. But we can have cache misses, meaning that we'll no longer have the zero latency. But I do recommend still utilizing Kafka here, because this way we have a complete backup of our database in Kafka. And it's really easy to put all of the events found in Kafka on a different type of database that maybe project the data like we saw in the first pattern to have a materialized view. So having Kafka alongside the database gives us a lot of flexibility. But if you have a small data set, you don't need a database. You can just use Kafka as the storage and have in-memory key value store. So the last pattern I want to discuss today briefly is the having events inside transactions. So usually we have the need to implement idempotent processing by ourselves in services, because we might need to process the same event twice because some failure has happened somewhere. Idempotency means that no matter how many times we process, we don't actually change the state. It remains the same. Now we can see how Kafka allows us to reduce a little of the burden to have idempotency and exactly once processing, that some of that can go and be found in the Kafka API itself. So consider the following classic e-commerce flow, where we have the payment service that produces the payment completed event to Kafka. And now we have the checkout service that will consume the payment completed event and will produce the order completed event along with all the items that were found in the cart and all the relevant details. And now all the downstream consumer services can start processing that the order was completed and do the needed action. Delivery service can start processing and making sure delivery happens. Inventory service will update the inventory to reduce the amount of all the items found in the order. Invoices service can start preparing the invoice needed with all the items, information, etc. Now, we want to achieve exactly once processing for the flow here. So we don't want the producer of the checkout service, for instance, to write the order completed twice for the same order, because that doesn't make any sense. We only want to process the order once. So if we look at traditional approaches to solve idempotency, usually it will mean that all of these downstream services will need to create a table that will have information on all the completed orders, including the order ID, in order to make sure when they get the event that they didn't already process it. So they'll need to write when they finished processing the order, and because they may get double messages or triple messages. So they need to make sure that they only process it once. So they start doing database tables, locking, etc. So with Kafka, we can have a different approach. We enable idempotent producer, first of all, and this allows to make sure that producing messages, the messages are produced exactly once by having the idempotent producer attach an offset, the index of each message. So it produces message 1 with offset 0, message 2 with offset 1, and then for some reason the producer didn't get the acknowledgement from Kafka, so it will produce the same message with the same index 1, and Kafka will identify that this index has already been written down and will just discard this message as a duplicate. Good. So that solves the original producer problem, making sure that it only produces exactly once. That's very simple and straightforward. Now, for the rest of the flow, it's a bit more tricky. We have a consumer that also produces, and we have downstream consumers. So here what Kafka offers is to have a transaction that is created for between the consumer and producer and downstream consumers. So this transaction means that messages that are produced that are part of these transactions will not be visible by the downstream services until the transaction completes. Only once the transaction completes successfully and was not aborted because of some restart issue, failure, only then will these services be able to start processing the order completed event and do what they need to do. So this way we guarantee that the order completed event arrives only once for these services. So events transactions are quite complex. You don't need to do a lot by yourself, like with the optimistic locking database table I mentioned, but you will have more boilerplate. You'll need to also tune the performance according to the transaction side, because bigger transaction means more latency, smaller transaction means lower throughput. And also, if you have third-party calls and also database updates on your downstream services, there can be failures when you process the message. So you still need to do the deduplication and the idempotency at the external edges found outside of the Kafka pipeline, because Kafka can only help you with what it has control over. But if you have a failure to write to some database, you still need to make sure that the data that you are, when you retry, that the data is not corrupted, that the inventory count keeps consistent. But what you can do is you can actually use the Kafka record offset as the version. So you can make sure that you don't needlessly update the counter if the same record offset has already been updated. So I don't recommend just turning on Kafka transactions by default, because it does have a little bit of a performance impact, and it means a bit more complexity for your code. But I would highly recommend using it in critical flows like payment processing, for instance, to make sure that you process the information exactly once, and everywhere money is involved, you want to get the highest degree of certainty. And if you want to hear more about how Kafka implemented the exactly once delivery and semantics, I have a talk I gave on a previous conference, so you can check that out as well. So what have we learned? We learned that Wix developers have employed all these patterns that I've mentioned: consumer project, event-driven end-to-end, zero latency key value stores, and transactions events to make their microservices more decoupled, resilient, and easily scalable. So thank you very much. And I have here all the resources for you if you're interested in more to learn more. I have the patterns I discussed and more patterns on my blog posts with links here, and a link to a great blog post series by Ben Stopford from Confluent on event-driven style of thinking about how we consume data, approach data, and microservices. And a great attachment to this is the wonderful article by Chris Richardson on the woes of shared mutable state in databases. And also, you have a link here to the talk I give on exactly once delivery with Kafka. So don't worry, I put all of the slides up on SlideShare. So all the links are up there. So you just need to remember this link, slideshare.net/Natan Silnitsky. And you can also follow me on Medium and Twitter to have to get updates on everything we do on my team at Wix around event-driven style, architecture, design, anything to do with Kafka that we have on our team. And if you want to check out previous talks I gave in conferences, you can see them on my website at natansil.com. So thank you very much, and I hope to see you on the QA session on Zoom. Thanks again.
Natan, hi, wonderful. Thank you very much for your presentations. Actually, for 2 presentations that you already did. Fantastic.
Well, thank you. I really enjoyed it.
Super. We hope that we will see you in the Q&A chat, first of all, and then we will see you next year at the Devoxx Ukraine conference. And I want to encourage everyone who is watching you to vote for your talk and for you as a speaker in our application. So please download and go to the application and vote for Natan. Thank you.
Thank you so much. I really appreciate it. And yes, see you next year as well, for sure. And now for the Q&A session.